All right. Well, while you're getting your slide up, let me just make an introduction to Gavin. So good morning, everyone. Thanks for attending on this fairly chilly day across the country. I hope you've got some warm stuff in the coffee you're drinking. By way of background, Gavin is a graduate of WITS, Witwatersrand University. We haven't had one of those for a while, so welcome, Gavin. And then Gavin started out as a diamond geologist for Cape Exploration, stroke De Beers, based in Kimberley in the Karoo. And then went on to work as a geophysicist for Anglo De Beers for 15 years all over Africa. He also lived in West Africa for 4.5 years as an expat, doing gold and base metal exploration with Anglo until they closed down in 2002. Since 2004, he's run his own successful consulting business for 17 years now, working as a geophysical consultant and doing contract work mostly in a company called Geofocus with his partner Bjorn. So thanks, Gavin. Thanks for the prep. Thanks for making yourself available, and we look forward to your presentation.
All righty. I'm going to share my screen. Just tell me if it comes up okay.
Yeah.
Oh, man.
Okay, come on.
Nothing happening.
The camera's off. Nothing yet?
Okay, I'm just going to come back in. Seem to have lost everyone for a sec. Let me just come back in.
Are you still there?
Am I still there?
Yep.
Yeah.
All right, I'm going to just stop my video and share screen. So let me know how this goes.
There we go. You're up. You can start.
I'm just going to get full screen now.
All right, so I'm not going to bore you guys with old technology. We all know magnetics and all that stuff. I'm going to talk about just two things today, which we've been doing at Geofocus. Extending the use of ground penetrating radar, which you've all heard of and obviously know about, and then drone magnetics, which is something we've recently got into. We're doing drone magnetics commercially now. We've done a few commercial surveys that have come out pretty well. And I think we're probably the only guys in South Africa, maybe one other. Edgar Stetler also has a drone, but I don't know if he's doing it commercially. So I'll start off with ground penetrating radar and explain a few things about the issues. Obviously, we know that it's used for engineering applications like finding water mains and cables that are buried and that kind of thing. These are very shallow applications, and generally those antennae have to make contact with a very smooth surface like a pavement, a tar or a road, or a concrete floor. In terms of doing geological exploration, that's totally unsuitable. Those are high frequency antennas and they only see down a few meters. So we decided, no, we're going to try and get into real geological work with an antenna that can see down tens of meters. We need to see deep, and also we need an antenna that doesn't make contact with the ground, doesn't need smooth ground, because you can't work in rough terrain with that. So all of the modern types of, or the first types of ground penetrating radar that come out are pretty unsuitable. So how does radar work? It's essentially electromagnetic technique. It's just EM. It sends out an EM pulse. You get a reflection, just like seismics. You convert that reflection time to distance, and that gives you the distance to the reflector, and then we kind of create a reflective surface, just like seismics. So you're bouncing back an electromagnetic wave instead of a sound wave. It depends entirely on the dielectric constant of what you're looking at. If you've got a very conductive layer, if we have a look at this diagram here, you'll see we've got a soil profile on the left. Hopefully you can see my mouse. What you need is not a harder layer as you would with seismics or a denser layer. You need a layer with a higher or a lower dielectric contrast. You see this E1 and E2, they're contrasting. And unfortunately, one of the downsides of radar is that water content raises your dielectric content a lot. Sorry, your dielectric constant. So much so that it will actually reflect off the water table, or it will reflect off a clay-rich horizon that has water in it, or anything like that. You have this antenna in a cart, you push it along the ground, you can see that this red antenna here is actually making contact with the ground. And that's what we don't want in geological work, for the simple reason that we work in very rough terrain. We're going to be walking through the felds, we're going to be walking over gravels. You'll see on the right here, what you get back is, just like seismics, you get a parabola. You don't get a straight line. And the reason for that is you're slowly approaching as you walk towards your reflector, or whatever it is that's giving you bounce back, you walk towards it, you get closer and closer to it, and then you walk away from it. And that basically makes a parabolic reflector, and then we have to undergo something very similar to seismics called migration, where we make that into a flat surface. We convert the time to distance, and then we can tell you how deep that thing is. But if you get your dielectric constant wrong, your conversion from time to distance is also going to be wrong. So one of the biggest problems, and we all know every geophysical technique has problems, the biggest problem is we don't know the dielectric constant. So ultimately, you'd like a borehole, you'd like to measure it, then you'd get it right. What we do from the start is we do kind of guesswork, and we say, oh, this is hard rock, so that's dielectric constant of 8. Or if it's tar road, it's a dielectric constant of 6. So we work with published values initially. But what you can do is you can then calibrate it on site. So you can stand over a known reflection, or an area where you've made a pit, for example, and you can tell me, okay, we hit bedrock at 6.5 meters. I can see it in this pit. Then I can walk over that area right next to the pit, and I can calibrate the dielectric constant to match 6.5 meters. So there's two ways. You can either measure the dielectric constant, or you can measure it with a known. So these are the type of things that we call utility work. You'll see engineers doing this all over the show. You'll see on the right, this guy even has a hand pushed one, and usually what these are used for is to find rebar in concrete. So for example, you're building a new Carlton Center, and the contractor says, oh yes, I did the rebar exactly as it says in the contract. I put in one bit of reinforcing every 20 centimeters. You don't believe him because the floor's cracking up, so you bring in this guy, and he can actually map how often that rebar was put in using that little guy on the right. Now, the smaller the antenna, the higher the frequency, the shallower it sees. So this guy on the right is looking very shallow. He's looking down 10 centimeters or something. Then we go to slightly bigger antennas on the left, and that guy's seeing down. He may be looking for pipelines, or he may be looking for cables. Now, the beauty of living in a chaotic country like South Africa is nobody has town plans anymore. Nobody knows where their pipelines are anymore. Everything's been lost. There's no competent people to find anything anymore. So we get tons and tons of work from town councils going, can you tell us where the sewage main is on this road? Can you tell us where this big buried cable is on this road? And there are so many people making a living from doing this now. That is fantastic. But we're not really into that. We are trying to do geological work where we can map down 15, 20, 30 meters. So this is what we call utilities work. And that's an example of what you might get out if you're looking at, say, a road base. You're trying to see how thick a road base is. You want to see if the contractor's done his job. So largely we use radar for quality control on roads. And if you're looking for a pipeline, you'll see the depth scale on the left. That's 50 centimeters, say. You see the perfect parabolic reflector from a buried pipe there. So now you would place the pipe right at the top of that parabolic reflector. You put it just under there, and you'd say that's where your pipe is, exactly 30 centimeters down, if you got your dielectric constant right. So just remember, with radar, you're nearly always looking for parabolas, and you can straighten them out, or you can leave them like that if you're happy to work with parabolas. So we decided, no, we're going to go into something that sees deep. So we bought that blonde lady, and then we bought that antenna at the same time. And we decided, okay, guys, that was a joke. You can laugh. We wanted to see deep, and we wanted to work in rough terrain. So we imported this antenna from Sweden, which is the lowest frequency antenna currently being made. It's at 40 megahertz. To look deep, you have to be under about 120 megahertz. And you'll notice now that how long this antenna is getting. This is now 2 basically 2 meters long, this antenna. And you pay the price. The trade-off is resolution, but you can work in rough terrain. So it's the usual thing with geophysics. You want to see deep. The instrument has to be bigger, but it's got less resolution. You want to see shallow. You can have a nice, light, small instrument. You've got very high resolution, but it doesn't help you because you're only seeing down 2 to 3 meters. So when people phone us up and say, we want to see such and such, we immediately have to know how deep this thing is, what the soil and the rock profile's like, and then we give an idea of maybe whether we can see this thing or not, and you know what frequency antenna you have to use. It's not unusual to approach a job with several antennas. Start looking shallow, go to a medium depth, and then go to a deeper depth. And then at the end of that, you've got an answer, and you can say, well, we lost resolution at about 5 meters, but at least we've got something down to there. So if you look here where my mouse is, we're talking 40 megahertz. That is about as low as we can go and see deep. It's called a low frequency antenna. And you can run it on something called a rough terrain cart with very big wheels, like 4x4 wheels. So we made this cart up. We bought a conventional cart and then we adapted it. And we actually run the antenna sideways through this thing. Obviously, all of this must be plastic or aluminium, so that because these antennas are only semi-shielded. Now, what shielding is with antennas is that you put lead on top of the thing, essentially, so you don't get any reflections from trees or building walls or anything in your immediate environment. You want to basically fire that electromagnetic signal, you want to pulse it down into the ground, and what you receive, you want to know it is coming from the ground, not from that wall over there, not from a car that came past, and certainly not from the trees above you. So this antenna is big and it's only semi-shielded. So you've got to be quite careful. Make sure you don't work next to fences. Make sure you don't go under power lines. So that's another issue with radar. Another big problem is that working in urban environments becomes a problem. Again, we targeted geological environments so that we are hopefully working in pristine felts where there are no spurious reflections. Our only issue would be trees, hopefully, and then we'll try and work in an area where there aren't a lot of trees. But this is partially shielded, so it doesn't see anything coming from directly above. It only sees stuff coming from the sides. So that's more or less what our setup looks like. And then on this goodie over here, you put your console. You'll have a big cable running to the antenna, and then you can push this thing along at walking speed. It's quite fast. That's one of the beauties of radar. Is as fast as you can walk, you're getting the survey done. You don't have to stand there for hours like a lot of techniques. So here's an example of what the guys who sold us this antenna have managed to do. This is a 70-meter deep sequence of sediments on the left, and on the right, they've managed to see down 100 meters. On your left, that's with a 70 megahertz antenna. On your right, that's with a 40 megahertz antenna, the very one we bought. And I think you'll agree with me that's not bad. We're seeing geology, we're seeing the base of a basin, we're seeing something that looks like vertical fault, which I don't believe, because radar is very, very bad at mapping anything vertical, just like seismics. You need sub-horizontal features to get bounce back. Otherwise, the signal's just going to run down that vertical thing. But you can see we've mapped another layer here. There may be something on top there. There's definitely something going on there. So this is decent geological work. This is down to 70 meters. It's a very shallow basin. And you manage to see something here, and it looks very much like a seismic section. So that's what you're looking at with radar. You're looking at something that looks like seismics, but be aware that this is perfect. These are perfect geological conditions. You just about never get that in Southern Africa because you always have soil overburden, laterite, calcrete, Kalahari sand, all the usual stuff that gets in your way in Southern Africa. Whereas when you're in Sweden and Finland and Canada, they're wonderful places to work, because glaciers have taken off all your conductive overburden and you're left with rock. That's ideally what you want. That's an example of what you can get out of radar with a deep seeing antenna in perfect environment. If I zoom in there, that's the kind of amazing detail that you can get if things are very, very good. You'll see that this is the SE40 antenna, 40 megahertz. And you also get a window that maps with the GPS. And I might add, you can run it with a differential GPS like we do, so you know exactly where that antenna is at all times. And it stamps, as you walk in along, it will stamp each one of these pulses with a GPS position. So you can plot up exactly where you walked. And you can actually do 3D surveys. So you can walk in a grid, just like a gravity or mag survey. Then you can plot all of those profiles up in 3D. And then if you've got really clever software like time slice software, you can start cutting down through that radar and you can start mapping surfaces in 3D. That's pretty advanced. First of all, you actually want to get signal and you want to see what the hell you're getting. So here's some real examples of alluvial gravels. And this is where the diamonds, a lot of requests we get are for diamond gravels. You can see the depth scale on the left of this image is down to 30 meters. That's pretty good for radar. We would consider that extremely good. I know that perfect example showed 70 meters. I would consider that extremely rare. If anyone tells you, like the Russians do, they always come along and they say, oh, we build the best stuff. You know, we can see down 300 meters and map your copper deposit. They're talking rubbish. It defies physics. It defies everything. If you can see down 70 meters, consider yourself the luckiest man in the world. If you see down 30 meters, that's phenomenal. More like 10 to 15 to 20 meters we consider good. Look at this top image here. We've managed to do some sort of phase processing. So where you've actually got alluvial gravel, you'll see some disturbance in the phase. So one of the clever things, just like seismics with radar, you can map is not only the time of that signal coming back, but what happened to its phase? Did it get delayed and did it get warped? So you can map phase changes, and you'll see how the gravel got highlighted here. This diamond alluvial gravel got highlighted in yellows and reds because its phase had changed. Then as we went out into bedrock, it's all blue, a couple of little disturbances, and then you'll see it's picking up on the right there of your screen where my mouse is. You're picking up some sort of phase change there as well. Could also be maybe an alluvial terrace or something over there, so it'd be worth looking at. So this is the kind of data you're trying to get. You're trying to do clever processing. If you look at the bottom, very bottom image where my mouse is now, you're basically using texture and linearity analysis, and where again you've managed to make the colors red and yellow, you're hoping that you've got your largest gravel boulders at the base of the sequence, and that may be the area of interest. So this is the kind of work we're trying to do. We're using the air-coupled antenna where you can walk along. It can power that pulse through the top 20 centimeters of air and then into the ground. It doesn't have to make contact. So that means we can walk over an Orange River alluvial gravel and we're not making smooth contact with the ground. Here's a real-life example of some gravel work and some kimberlite diamond, some diamond work that we did. This is alluvials near Bakerville, Lichtenberg. So if Mike de Wit's on this group, he'll be thrilled to hear it. I'm not going to show you exactly where. Obviously, this is classified work for other clients. I can't just go telling you all the graphs we've done. So nothing's got coordinates on it. That's near Bakerville. And what we wanted to do was map out some of these gravel runs. Now, everyone knows around the Bakerville area, the alluvial gravels are constrained in runs, which look like eskers or they look like river gravels. And they occur in these linear, sinuous features, and often they're buried in karstic features. So this is all on dolomite. And what happens is that a lot of the gravel's been removed in places. Some of it stands proud on dolomite, and you can see it standing there, but other gravels are actually buried under the ground, basically covered, and they're in karstic features. So you'll see this is one of the runs, the yellow and brown there, and this is a run, this green thing here. And obviously the guys who have this piece of ground want to know where there's more gravels on their ground. So we did two things here. First of all, we flew a drone magnetic survey for them, very low level. It's nice and flat there. And we mapped this dike that we didn't know about. There's a dolerite dike screaming through the area. But another thing we wanted to do with the drone magnetics, because we're so close to the ground, is map these disturbed areas. Why? Because we believe some of the ilmenite and sometimes there's a little bit of magnetite, but mainly ilmenite, heavy minerals in the gravel, sometimes cause there to be a slightly disturbed texture in the magnetics. So we did this as a first pass, and we wanted to see, okay, have we got some disturbed areas? And you'll see, if I could get my mouse to work, and there it is. You'll see there's a disturbed area up here, there's a disturbed area up there, and there's some disturbances down here. So we labeled these areas Area 1, Area 2, and Area 3. Obviously, we're using the Google Earth images as well, everything they've given us, any mapping they've done. But we use this magnetics as a first pass. And then we clearly saw on the Google Earth image that there are very linear looking features in those areas that have got linear vegetation anomalies on them, but they're not dikes, they're not magnetic. All we saw were disturbances there. It didn't look like a dolerite dike. And you can see on the left of this image that there's some kind of digging going on here. It's in the next farm. And what I'm showing you here with the blue traces on top of those linear vegetation anomalies is very shallow seeing EM we did. And you can see that we're getting little blue peaks over these vegetation anomalies. So they're slightly conductive. There's a little bit of magnetism in there. We're starting to suspect that these are karstic features. There may be cracks. There may be dikes that are non-magnetic, but we don't think so because the other dolerite dikes in the area stand out really, really well. So these are interesting features. You ask yourself, why are they running parallel to each other, spaced like that? I don't know. There may have been cracks in the dolomite, and then they become dissolution features and they become karsts. So we said to the guys, this looks promising in these two areas here, area 1 and 2. What we're going to do is run some EM. We're going to run some radar over these areas, and we'll take a look and see what those two things show us. So we did some radar and we did some EM over those two areas. You're looking at a color image of the magnetics there again. So you can see we're running parallel to this dike. That's the dolerite dike there. And then we did these radar lines and EM lines labeled 6, 7, 8, 9. And we plotted up the EM, the shallow EM, and you can see that on the left here, it's pulling out those linear features I showed you as the blue traces. And it's pulling out a couple of very ugly looking linear features here on the right as well. These ones run north-south, that one runs north-south, but this one runs sort of east of northeast, that one runs east of northeast. So they're corresponding to those features we saw in Google Earth. And now we start looking at the radar traverses. Now you'll see with our deep seeing radar antenna, you don't see anything down to about 2.5 meters. It's just muck. The reason for that is the very low frequency that the radar works at. And a good rule of thumb is if your radar antenna is 2.5 meters long, that's the distance between the receiver and the transmitter. And that means you're not going to take any data 2.5 meters deep seriously. You just see these black and white lines. That's fine. We know that. And you'll see the depth scale here on my left. I've used the dielectric constant of solid rock, dolomite around about 8. It's a first pass guess. And we're starting to see immediately after 2.5 meters deep, we're starting to see interesting stuff. We're seeing these rippled features in the radar. And funnily enough, that's exactly what chert looks like inside radar, inside dolomite, and dolomite very, very reflective. It's obviously very hard. And you'll see that I've set the depth scale to 10 meters because this is the kind of depth these guys want to look at alluvial mining. What's interesting is we see dolomite, solid reflectors, and then suddenly at distance, what you'll see distance in meters is marked on the top here. And that will have a GPS track associated with it on the right. From 135 meters to 155 meters, in other words, 20 meters wide, we see the sudden clear patch. And this sudden clear patch, as I'll show you, actually corresponds to where we had those little electromagnetic signatures coming out, slightly more conductive. So these are karstic features. They holes, if you like, in the dolomite, and they're filled with either soil or gangue, I mean not gangue, wad, magniferous wad, or perhaps gravel. We're not seeing anything that could be gravel, I admit, but we are seeing a gap in the dolomite, and it's much, much clearer to me now that this is a hole. It's a karstic feature and needs to be investigated. Here's another example where this clear gap is only 10 meters wide. It's running from 55 meters to 65 meters on the traverse. You can see incredible textures, sloping textures in the dolomite and the chert here. You can even see little fold structures. I've absolutely no doubt that those are dolomitic chert features, and the radar is faithfully mimicking these layers of chert that it's seeing in the dolomite as well. Anyway, another interesting feature for them to look at, we're going to plot those up on a Google Earth image, see where they occur. So I'm taking these features now and I'm going to overlay them. Here's your GPS track on the right. And this is quite interesting. This is not a perfectly clear area. You'll see it has some reflections in it. It's not the same as a solid dolomite, but from about 10 meters to about 30 meters here, we're seeing a different area. It's got some reflections in it, radar reflections. So this may be something more like gravel. This may be coarse gravel giving us reflections, or it may just simply be a karstic feature that still has chunks of dolomite in it, or boulders. We're not sure, but we know for one thing, it needs investigation. Here's an example of perfect parabolas. Now we've got into a very soil-rich area. This is thick soil down to 8 meters there. And suddenly we're getting all these clean parabolic reflectors. So this is not your average dolomite. That's not your dolomite signature at all. What these are, we believe, are big boulders at depth. Each one of these parabolas is showing us a large boulder reflection. And you'll see your depth on the left, they were down at 3 to 4 meters. One of them is down at 6 meters. So I can just read clean off along these lines to about 6 or 7 meters. So what the hell is going on here? We don't know. We know that this is a very, very thick soil. We're getting just about no reflections except where these parabolic guys are coming in. They look like boulders at depth. Does that mean there's a gravel in there? Not sure. No harm in putting a trench in there and taking a look. That's the kind of advice we would give. We're not soothsayers, we're not magicians. Can't say it's a gravel, but we do know that something big is giving us individual reflections there. And another area, quite interesting area, where we're getting lots of individual parabolas, but surrounded on the left and the right by soil. So what is going on in there? Again, your GPS track. And if you run your mouse anywhere in this radar reflection, it will tell you what your GPS coordinate is in UTM, because that's what you set it up. So if I'm just moving my mouse along here in the software, you'll actually see the mouse moving along here, and it'll be spitting out a GPS coordinate at all times. So everything is tied together. So the guy says, yeah, but where exactly is that? I'll give him a GPS coordinate. These black lines on the EM response show where we saw those features in the radar. And there's absolutely no doubt in my mind that if you look at that black line there, the next line across that black line there, that black line, they're corresponding with these slight conductive features in the EM. So we've got three things agreeing with each other now. The area is magnetically disturbed. On investigation, we saw that there were linear features and vegetation features. We now know they're slightly conductive, and we now know that they are holes in the dolomite. So they are, in fact, probably channels. Is there gravel in that channel? I don't know. We're going to have to put trenches across here or drill. There's another good correlation. EM feature, nice radar feature. Nice long radar feature there, worth looking at. And there, where we only did, now these guys didn't have a big budget. We should have done more EM and better EM. But they're poor sort of gravel diggers. They just wanted us to have a quick and dirty look. Here's a lovely EM, what looks like a channel. And we're getting some radar reflections there. Not as clean as this side. This side is giving us a much stronger correlation between the black lines and these red responses, EM and radar. So this area looks very promising. And then we obviously recommend it. Go and take a back actor and put trenches clean across this feature. Sorry, just go back there. Take a back actor and put trench clean across this feature here, clean across those features there. And that's just another picture which shows more EM overlaid on mag. Actually not sure why I even put this in. Oh yeah, to show where the radar responses were black again, there, and there. And you're seeing the EM response in blue, a bit messy. But it's interesting how our sort of gut feeling that ripples or texture in the mag is leading us into the right area. They're not dikes. They're something else. They're karstic features. Now we know that karstic features in the Luxembourg area are filled with manganiferous wad, and actually they are slightly magnetic. So mag is not a bad way to go in this area to bring you into the right area and start looking with other things. So that was a real life example of how we used drone magnetics initially, and then we went to the radar, and the radar gave us a hell of a good idea of how wide these features are. Much more accurate than the EM. The radar was telling us exactly from 15 meters to 25 meters, there's a hole in the dolomite here, you need to trench that area there. So the radar did a very good job here, and it's probably the best results we've ever had with radar is on dolomite, which tells you that it's a hell of a good sinkhole mapping tool as well. And a lot of work that we do at GeoFocus is geotechnical, where we do try and find sinkholes in urban areas. And the radar is indispensable. It maps sinkholes beautifully, particularly if you've got dolomite walls, and then you just go into magnetiferous water or air or water, then it shows it up nicely. Henny, are we going to have questions now on the radar, or should I finish the drone section and then we have them at the end?
I think carry on, Gavin, and finish, and then we'll have a good discussion session.
May I ask one quick question before we move on?
Okay.
Yes.
Gavin, how is it that the radar gives you a series of reflections, all those lines? I would think if it hits one barrier, it'll reflect and won't go any further. How can you get a whole series of reflections?
Generally, it depends on what you've hit. If what you hit is very, very conductive, like clay with water in it, you will only see one reflection. But radar has a horrible habit of repeating that reflection. So, like seismics, you do get a delayed reflection, almost like a harmonic. And then you'll see that reflection repeated at depth, exactly 2 meters apart or 1 meter apart. Then it'll repeat weaker again at 1 meter apart. If you're aware of that, you can get rid of it, take out repeat reflections. However, if it's not a very strong reflector, like a clay-rich horizon with water in it, and it's something like dolomite, where it just seems to bounce back off some chert, but part of it passes through. So like seismics, you'll get some of the wave reflecting back immediately, but some of it passes through. And then you'll get a second reflection off a second layer. So what I'm saying, to sum up, is that a strong conductive feature with a high dielectric constant will only reflect once, and then if you're aware of its multiples, you'll get rid of them. However, certain types of rock allow it to pass through and see a second reflection of something deeper down there. And you'll see on that example that I gave from Sweden, those guys managed to map at least 2 geological features there. So they had perfect geological environment, and they managed to do that. So it all depends on, I won't say luck, but the geological environment and how lucky you are to have a decent geological environment. Sometimes you do see 2 or 3 real reflections down there, only because that environment allows that pulse to pass through and reflect off a second layer. So forget about it if you've got something. If you hit a clay layer, forget it. That's all you're ever going to see. But in some environments like dolomite, it allows you to see through and see more than one geological layer. Should I continue, or another question?
Carry on.
Right, so the second thing I'm going to look at is drone magnetics. Now, why only magnetics? Well, the magnetics so far is the only thing that we've managed to make light enough to go on a drone, a small drone. Obviously, we'd like to put every single geophysical technique onto a drone, but we're still in the process of miniaturizing everything. Mag was the obvious one to go first, and obviously I'm not talking about photography now, because I don't consider that geophysics. And digital terrain models, you might consider geophysics, because we use an altimeter. So far we can put an altimeter and a camera on a drone, we know that. But what's new is putting actual geophysical instruments onto drones and flying them just above the ground. So they're like mag surveys on the ground. Sorry, they're like ground mag surveys. But the beauty of these things is we can do them hell of a fast, and we can cover rough terrain, and we can go over landmined areas, and we can go in areas where people shoot at you, and all of that's much safer now. So this is a picture of the kind of drone that we're using. You can use a 4-copter, a quadcopter, but I'll go into the reasons why you use a 6. So what we consider ourselves fairly pioneering in this field. As I say, one of the only 2 people we know who have this set up in the country. And I think we're the only people who've done commercial surveys, actual paid for surveys, and we're busy getting requests all the time. People are quite interested. I'll go into the costs and all the issues now. The drone we're using is called a Matrix 600 Pro. 600 refers to 6 props. And we use licensed professional pilots. We don't bother trying to learn to fly this thing beautifully ourselves, because our job is to deal with data and interpretations. So I think we did something quite clever there. Instead of trying to get our own licenses and get our own drones and all that, we said, no, we'll JV with people who already have licenses and already have very highly trained pilots, because it's quite formal now. You have to have a permit every year. You have to undergo qualifications. And to keep all that going every year is a pain in the butt for us. We want to just operate that thing hanging down there, that bird. Now, obviously, we have to hang that thing quite far down, because this drone is giving off an electromagnetic response, and there's metal parts in it. So it's very simple to do test work, and you just say, okay, I tried 2-meter cables, I'm still seeing noise. Okay, 3-meter cables. Obviously, the cables have to be nylon. Everything you fix to it has to be nylon. There's nothing magnetic on that bird. That thing is extremely, extremely sensitive. The bird is called a Geometrics mag arrow. They're available off the shelf. They cost a lot of money. They're made by Geometrics in Canada. I'm going to show you quickly a video just to excite you and show you what they look like of us flying one. This is what they look like when they're flying. That's how low we can fly over the ground. I'm just going to show that again. You'll see that we use spacers on the string or the nylon. Okay, don't worry about that noise in the background. That's a pilot. And here's another good example. This is perfect drone country. So now we're flying at 7 meters. We were previously flying at 2. And that's what this whole thing looks like. So now you know what I'm going to be talking about. And the beauty is you can just rotate it in the air like that. These guys are really good. You just turn it online and off you go again. And you can see the arrow, the actual arrow is designed to fly into the wind nicely. And, you know, it's basically aerodynamically designed. Okay, so our platform, as we call it, is the DJI Matrix 600 Pro. It's called a hexacopter. It can carry, it weighs 15 kgs, but it can carry 5 kgs of weight.
Gavin, just go to full screen again.
Oh yeah, sorry. Its lift capacity is 5.5 kilograms, but that our drone, I mean our bird. So when I talk about the drone, I'm talking about the copter. When I talk about the bird, I'm talking about the actual magnetic instrument that hangs below it, the mag arrow. That mag arrow weighs 1 kilogram, and that is the huge advance that has happened that has allowed us to go to this drone magnetics. This thing can fly along at 65 kilometers an hour. It can take wind to a degree, not too strong. It can fly very high, obviously, but there's no reason to fly high. We want to fly as low as possible. It can take a wind resistance of 15 knots. And what you have to do, there's 4 batteries inside that drone, but to fly a survey, you have to have at least 6 sets of batteries. So that is 24 to 30 batteries. Each one of those batteries costs in the thousands. They're obviously lithium polymer batteries. They can recharge very, very fast, but they're expensive. And to do a proper day's work, you need to have 30 of those things on standby. And then you have to have a whole charging setup in your 4x4, whereby you have a fridge to cool them off while they're charging. You blow a fan on them. And the whole time you're changing batteries and you're charging batteries and you're keeping batteries cool. And you're cycling through those batteries. Because the biggest problem we have with the drone at the moment is it eats batteries. You can only fly for about 25 minutes. So if you want to do a day's work, 8 hours of work, and get a survey done chop chop, you need to have 30 batteries and you need to have full charging and cooling capacity. We can put an altimeter on, a proper laser or radar altimeter onto this thing. They're very small. And then we sling the mag arrow 3 meters below that thing, and we fly about 10 meters a second. So that's a lot faster than walking ground mag. The speed, we cover the ground 7 times faster than ground magnetics. Our average production is 60 to 70 kilometers per day. We could do 100, and that's what we're aiming for, and we're just getting better and better. The beauty is we can fly over swampy terrain. We can fly over rivers. We can fly over areas where garimpeiros are working the gravels without them threatening us, and also not without us walking up and down in their pits. So we do quite a bit of diamond gravel work as well. Again, working on the theory that ilmenites in the gravel are going to give you some sort of a ripple texture. We can definitely work in dangerous areas. In fact, landmines, any kind of barbed wire, that sort of thing is fantastic for a drone. And recently we worked for free for the Kruger National Park, trying to locate snares, very big snares for hippos and elephants. They are thick cable. They obviously are steel, so they do have a magnetic response. And they wanted us to cover heavily snared areas in the northern Kruger Park, cover a lot of ground quickly. However, the tree cover was high and we couldn't get low down enough. It's impossible. In order to see a piece of wire with a drone, you have to get down to a couple of meters. And if there are trees there, you can't do it. So ultimately it failed, although we proved concept that if it's on the ground and we can fly 2 meters above it, we'll see it. But it's not realistic to fly 2 meters above trees or above the ground where there are trees. The other thing is, if you fly 5 to 10 meters above the ground, you actually get a much better data quality than ground mag, because a ground mag antenna is just above the ground. It's 2 meters above the ground. And you pick up every little noise ripple from laterite and from fences and all that stuff. Which if you get a little bit off the ground, you actually get better data quality. So what about the costs of flying this thing? They're the same as ground mag, 700 to 1,000 Rand per kilometer. However, they're much more expensive than flying airborne surveys, mag-rad surveys with a company like Excalibur. Excalibur charges less than that with their crop sprays. We cannot compete with that for the simple reason that our drone pilots require this amount of money to fly those things daily, and already that puts us out of the league. But we compete with ground mag. So what you're seeing now, what you're hearing from me is that drone mag fits into the gap between ground mag and flying big surveys with an aircraft or helicopter. Excalibur will never mobilize for a tiny survey, neither will NRG. So they just go, well, we're not flying that. And often it's an area that's very big, will take you months to walk with ground mag, and the drone fits right in the middle there. Beautiful. Faster than ground work, the data turnaround is almost immediate. We fill that gap between ground and fixed wing surveys, and we do medium-sized surveys. The problems with drone, there's a rule called line of sight that nearly all governments have instituted because they're trying to regulate the drone industry, and they're trying to make sure we don't fly anywhere near airports, obviously, and spy on bikini-clad girls and stuff. But also, they're trying to make sure that the drone does not run away from us and something happens to it out there. So they have a rule called line of sight. And in other words, if you can't see your drone, you have to turn it back. Now that is a complete pain in the butt, as you can imagine. If you're working in a very flat area in Botswana, you either have to build a tower, or you have to put a tower on the back of your bakkie or something like that, or you have to survey in small blocks, tiny blocks, and then stitch all those blocks together. So often, if it's flat, we have to fly in small blocks. Trees are a huge issue. We did a survey in Angola where we flew smack into a tall tree, and we absolutely destroyed the drone, the actual drone itself, the hexacopter, and its camera. Now, what happens when you destroy the forward-looking camera is you can't see trees coming up. So the drone becomes blind. So you can program it to fly, sure. But if there's suddenly a tall tree, like you get in areas of Central Africa, and those trees are tall, up to 80 meters tall, the pilot has to be extremely on the ball and concentrating. And he actually watches that forward-looking camera the whole time on a big screen. And if he sees a tree, he can override the automatic pilot and quickly go around the tree. You can imagine this is quite stressful work. And if he doesn't do it in time, you actually fly into the tree. And that's what happened to us. Then the camera was buggered. We couldn't replace it in Luanda. It took us 10 days to get a new camera up there. So you get huge issues like that. We're still struggling with battery life. It's still 20 to 25 minutes, and you need 6 to 8 sets of batteries, 4 at a time. Costs a lot of money. We are going to trial hybrid battery fuel drones. The trouble with those are they tend to be fixed wing. They tend to look a lot like American warplanes. So you get a lot of undesirable interest from military in a place like Angola, whereas if you fly a little hexacopter drone, it does not look military. So they're harder to get permits for, they look more military, and also with big plane drones that fly fuel, the line of sight becomes even more of an issue. I mean, you can't have this basically jet plane flying along and having to turn it back every 1 kilometer. It's insane. So all of this needs to be addressed, and it's all in its infancy. That's what the bird looks like. It's about 80 centimeters long, fits into a nice carrying case. And that's what its magnetometer looks like. It's the size of a 5 Rand coin. Absolutely amazing. It's called a microfabricated atomic magnetometer. And obviously, the beauty of this thing is its size and its weight. That's one. They put 2 of those in the bird. And what's awesome about that is if you have any kind of failure, then you've got backup because they're both reading all the time. And often you can change the angle that they intersect the magnetic field with. So if you're near the equator, you can have one perpendicular and one parallel to the field, and one will give you better readings on this line, and one will give you better readings on that line, depending which way the drone is flying, because you have to couple with the magnetic field properly. So it's fantastic having 2 of those in there, and the surety of knowing if one of them has failed or is spiking, the second one is probably working. And you can compare the 2 to make sure they're working. How does it actually work? Okay, the Mag Arrow has 2 MFAMs, microfabricated magnetometers. They're extremely lightweight. We have a GPS in it with 1 meter accuracy, contains this Bosch gyro, plus a Honeywell compass, and the operating temperature is kind of below freezing, -10 to 40 degrees Celsius. So -10 could become an issue if you're working in the poles, I guess, but luckily we don't do much of that. The other thing is, it doesn't say here, for some reason I left the most important thing out. This thing samples, when I say sample, it takes a reading 1,000 times per second. It samples at 1,000 hertz. Now that makes this magnetometer very, very, very special. That means you can fly it as fast as you want, and you've still got millions more readings than you need. But it also tells you that when you fly over something electromagnetic, you will actually see the electromagnetic response as well. So it has all sorts of kind of technological advancements that I probably won't even go into here, but it's absolutely amazing that it will take 1,000 good readings per second. And that's what makes it so expensive. Here's a real life example. Again, it's going to be diamonds. This is an area 1.4 kilometers by 2 kilometers. And we're going to fly it. The area we're interested in is this white outline. And all of this yellow stuff is power lines, quite high intensity power lines. They're mega voltage. And there's a substation. So you can imagine that on the ground, this would give you a lot of problems with mag. You would only get decent survey in there. But to be honest, it's the same with the drone, but the drone handles this much better. We can fly over or under those power lines, and then we can just cut it out, and it looks fantastic. So this area would take you at 25-meter line spacing about 10 days with ground mag, and you'd get a lot of surface noise. There's houses in here. There's all sorts of infrastructure. The drone handles the infrastructure noise much, much better. And you'll see that there's actually diggings here as well, and we're able to just fly over those with impunity, and we're able to fly under these power lines with impunity. So we tend to reduce the surface noise by flying at a certain height, and it took us 2 days to cover that instead of 10. That's the example of what it looks like when you're done. It looks just like any high quality survey from Excalibur or anybody else, but it's just much, much quicker than ground mag. And you can see that we actually just managed to cut out the power lines and the substation so easily, and there's absolutely no noise effect from those things. We're seeing this dike amazingly well. We're seeing these cross-cutting dikes amazingly well. And we're seeing 2 kimberlites down here. These are actually kimberlite pipes on kimberlite dikes, standing up very, very nicely. Again, that scale there is 2 kilometers. I've cut all the coordinates off. And we are able to do immediately, like a day after we've flown the survey, we're able to give the client all these products, reduced to the pole magnetics, which is showing you exactly where your kimberlite pipes are, where these dikes, kimberlite dikes are, where these dolerite sills are, which are very important in this area, and you can map the dikes in beautifully, just like any mag interpretation. This is analytical signal. These are the kind of products we deliver within a day. This is the first vertical derivative, and it's showing you particularly well these sills. And there's a sill coming off the dike there. But also now it's really, really homing in tightly on the dikes of interest, the kimberlite dikes. And if you look at this guy down here, that is an elongated pipe or blow on a dike. This guy's a very circular kimberlite pipe. And when we go to the second vertical derivative, we really home in on how small that feature is. There it is down there on the right. We're starting to lose the surface expression of this guy here because there's a pit there. But we are really homing in on the kimberlite dikes now, and the sills stand out better than ever. So it becomes a cinch to then interpret this thing. Don't know what, okay, there I start interpreting. This is done within a day, and I can start drawing these polygons onto this in Geosoft. There go my dikes. There I put a ring around the sills. I have these sills and dikes coming off the dolerite there. Interestingly enough, there's another little feature up there that nobody knew about that looks very much like a little blow. Kimberlite blow. It looks almost identical to that guy, just much smaller. So we mapped it in with some potential. Go and have a look at that, please. Don't know what it is. And it's interesting because this area is full of dolerite. In fact, the pipes are full of dolerite. So we managed to pull out, at least interpret what we believe is dolerite versus the strike of the kimberlite, which is all east-west. So everything that's east-west, we said, okay, we think that's dolerite, kimberlite. And anything that has the northwest angle on it, the northeast angle on it, and looks sill-like, we put in as dolerite. And so hopefully we gave these guys something very positive to work with there. And obviously they've got to go check this. We're not going to be right first time, but at least we gave them some really good information to work with. And that's what it looks like at the end of the day. There's the one kimberlite pipe, and there's the other. There's this interesting guy up here, don't know what it is, and then all the dolerite mapped in the grays and the blacks to differentiate from kimberlite. There's obviously a zone of gray where it's not clear over here, where this is going to be kimberlite or dolerite, and you could even argue about those, but it's fair enough. You just go and have a look here on the ground, put a trench across it, you'll have your answer, chop chop. Okay, what about other uses for drones? Well, firstly, we have to go into the fuel hybrids. Sorry, spelling. We need that longer range. We want to get away from the battery conditions, but we need to get away from the line of sight rule. That's a pain in the ass. We can do high-res photography already and video, obviously. Digital terrain models, very accurate because the drone has an altimeter and you've got an accurate GPS. So you know exactly how high your drone is and you know exactly how far it is from the drone to the ground. So as you're flying along, this altimeter is measuring many, many times a second, and you come up with an actually very accurate digital terrain. So often when we do diamond gravels, we'll do a very accurate digital terrain for the guys as well, and it just really highlights the areas where there's diggings quite nicely. Frequency domain EM is coming. It's already been tested with a very large drone where we can sling a small frequency domain EM instrument under a big drone. It looks exactly like the mag arrow, except it's 10 times as heavy and probably 5 times as big. But then again, you have to fly it very close to the ground. And because it's frequency domain, it's only going to see very shallow. So it becomes good at mapping shallow features, but we still haven't got anything that can map deep features. But the big one is hyperspectral. Hyperspectral scanners or cameras are already available. You can buy them off the shelf. So we're going to start offering hyperspectral. And obviously it's a specialist task to map that because you're in the infrared, but you can map alteration. You can map kaolinites, you can map smectite clays on surface. Huge applications for gold. And even, funny enough, things like the wine industry, soils, where you can map the right kinds of clays in the soil and tell the guy, right, this is a Chardonnay area, this is a Sauvignon Blanc area because it's got the certain kinds of clays in the soil. And I'm not just joking about that, that's become a very real application in California. So we're going to look at bringing it to the South African wine industry. So that's the future for drones, and that's the end. Thank you very much.
Thanks, Gavin. Good stuff. So I see why you're moving to the Cape.
Yeah. Yeah.
Okay, so people can turn on their their cameras and unmute themselves, please. And then we can go with the questions. But what your kimberlite locality at the end, will have a competition as to see, you know, where it is. But what was interesting, and Jimmy talked about it the other day, was the obvious in echelon arrangement of those dikes. So if Jim's there, he can comment.
Jim not there.
Jim left.
Gavin, you said that the drone cuts out the surface noise much better. Is it in the design? Is it the shielding? What makes it specifically better?
Well, first of all, you're flying a bit above, further above the ground, so you can get above things like fences that are very annoying when you're on the ground. So fences and the houses and things become a non-issue because you're above them considerably. So you actually lose that signature quite quickly. And then because it samples so fast, because of its design, it measures a very narrow noise signature. So whereas with a mag, if you're walking along with a mag and you took, say, a reading every 5 meters, you would have to cut out the readings that were noisy for this 5 meters plus that 5 meters. But because the drone has taken a reading every 20 centimeters or every 10, you can cut out much less of your data and cut out the noise precisely and still have real data. So it's because of its fast reading rate, basically, and its height.
Yeah. Thank you very much. Jim, you got that question just now?
Yes, sorry, I wasn't on. I was unmuted at the time. The in-echelon arrangement there, it's very nice when you look at geophysically. They look very small and very erratic. The simple answer there was, would they be economically feasible? And the answer to that probably lies in that the diggers have not done any work there. There's no disruption of the stuff there. So there might be kimberlite there, but it's probably dubious whether it'll be economically interesting.
Yeah. Thanks, Jim.
Dave Apka?
What is that?
You put your hand up.
David's still muted.
Unmute yourself, David.
Sorry about that, guys. Gavin, that was an awesome talk. Thank you. I really enjoyed the drone stuff. And just one non-geological question is, how do you move all those batteries around through international borders or even fly with them?
No, that's actually an amazing question. You're probably the only guy who picked up on that. Those batteries cannot be flown by airlines. They refuse to take them because of the risk of lithium being exposed to the air. It ignites. So you've got two choices. You can either get non-lithium batteries, which is not an option because there are no really good batteries out there. Lead acid, same applies. So the issue is you can't fly them. You can't even DHL them. So the answer is you have to drive them. You have to drive them across borders. Our guys drove to central Angola from Pretoria in 2.5 days. They were on site. So we don't mess around. We just chuck everything in a car and we go. And we just bullshine our way through borders. And you'll be surprised. Those borders are open now. South Africans don't even need visas for Angola. We get a 1-month free entry now. So Africa is really opening up. And basically we drive. We'll drive as far as Tanzania probably. West Africa is an issue. I don't know. You would have to buy the batteries there and add that into the quote. Or I don't know what you would do. It becomes a real problem. You're right, Dave.
Thanks, Gav. Yeah, no, I know it's a problem because I have an e-bike and the battery's out of consideration traveling.
Okay, so you ride it to Joburg to see your grandchildren, David?
No, I put it in the van, John.
Okay. Right. More questions.
Yeah,
Gavin, I'm still baffled about the layers. You talked about the 2 layers, but some of the diagrams you showed us had a whole series of bands on it. How does the radar pick up a series of bands?
I think a lot of those are reflections. They're multiple, what we call multiples. So it's the same reflection, it's the same band showing up again at later time and then showing up again at later time. So just like with seismic, you have multiple reflections. This thing has kind of a harmonic where the very first reflection shows strongly. Then you get a second one coming at twice the time, and then you get a third one coming at 3 times the time, and so on. So you get multiples that are not real. They are artifacts.
But you can still do an interpretation, you know, of the geology if it's not too complex, Gavin.
Yeah, it comes down to calibration. I mean, often you would ask a guy for a pit to calibrate on, something that can help you. Like I say, we're not magicians. You need a lot of help to calibrate. You need borehole logs to try and help make sense out of the thing. And to tell the difference between multiples and a real reflection is often a problem. They are tools. I mean, we have software. If something comes in at exactly double the time and triple the time and 4 times the time of a reflection, we automatically assume it's a multiple because it's precisely a real factor, a real figure multiplied. That's why we call them multiples. So if something comes in at 2 seconds, the one that comes in at 4 seconds exactly, we tend to assume is a multiple.
Okay.
It's not easy. It's difficult to interpret this stuff.
Okay, but I mean, the encouraging thing, you know, particularly on gravel, if you start looking at potholes and features and waterfalls and that, you know, if you've got decent basement geology, you'll see that and be able to put a picture together quickly.
Yeah, exactly. So the only thing you can really say you can map is the first really competent layer. Yeah. If there's nothing that's clay, water rich in the way. So if your gravel is nice clean gravel with silt and not a lot of clay, I know there's often clay in gravel, then the first thing you'll map is the basement, the actual hard rock beneath the gravel. And that's what you want because it shows you the channel.
Yeah. And have you done work on the Middle Orange River or down sort of Douglas, Prisco, that area? That would be very interesting. Okay.
No, we haven't yet. We've discussed with clients. We're always in discussions, and sooner or later we're going to do it for sure. What I always recommend is a trial run. So I'll tell the guys, look, just give us 1 day and we'll do test work. If the tests show up and you're happy with what you see, then we can go ahead. But if they're not good, then all you've lost is 1 day of work.
Yeah, we must connect you to some of those bigger operators. Okay.
Yeah, Gavin, I was wondering, another logistical question. How are you going to get round this line of sight limitation? Is there any discussion with governments or even the South African government about a sort of permitting system, say for one-off permits for surveys or something like that?
I think that would be exactly it. You would go for a one-off permit, so it would never be taken away as a rule, but you could possibly get a special permit for a survey by applying. Countries like Nigeria don't actually have it. We've been quoting on some really big drone surveys in Nigeria because they don't have the line of sight rule. And the other thing is that all drones are programmed, unless their battery runs out, they're all programmed to return to home the moment they lose signal contact with you. So these drones are very clever, and there's some very, very clever people who have thought a lot about how they work. So if you send your drone out over the sea and you don't have line of sight because you can no longer control it, because that's when you lose control of the drone, is when a mountain gets in the way. The drone immediately stops flying and it returns to base. It's got a return to base default, which is always set. So they are safe. The only problem you can really have is this thing runs out of battery power while it's out there and it plummets to the ground. That's what they're trying to avoid. But none of us want that to happen. So once we get to a stage where governments are trusting enough to say that, look, these are responsible operators, They're never going to allow it to happen. We can get one-off permits. But for now, governments are completely ignorant, as usual. They don't bother to get anyone up to speed with how these things really work or to talk to us. They just want to make money out of the permitting without really knowing what it's all about. So all they want to do is immediately slap a tariff on it and say, you can't fly without going through us. You need a civil aviation permit, and it's going to cost you thousands. But then when you start asking questions, they know nothing about it. So it's the usual, and it's dealing with governments that's a nightmare. I mean, we try to fly in Zambia, and Zambia just put a 2-year ban on all drone flying because they wanted to get legislation in place, and it would take them 2 years to get it in place. So instead of allowing it to happen, they just said, no drones whatsoever for 2 years while we're trying to get some legislation in place. Then with First Quantum, we tried to do a survey at, what's that nickel deposit, Ravensthorpe, and again, we misinterpreted the line of sight rule, and government shut the survey down. So, you know, you just have, because they'll send an observer to check on you, and our sort of line of sight was where we figured that line of sight would be where you lose contact with a drone. And they were like, no, if you cannot see it with a naked eye, and we were seeing it with binoculars. So line of sight becomes a gray area when you say I'm using binoculars versus I'm using my eyes. The other way to get around it, and what's quite clever, I think what we've done is quite clever, is we have spotters. So if we want to do a survey that's 5 kilometers long, survey line, we will actually put 3 spotters on hills in the area, all in radio contact. So if spotter 1 can see the drone, we consider that line of sight, even if I've lost it. And as long as we're still in control, I mean, we know immediately we've lost comms of the drone, but you can fly for 5Ks without losing comms of the drone. But spotter 1 can see it with binoculars, and as he's losing it, he tells spotter 2, I'm losing it, and spotter 2, who's further into the area, goes, I can see it. So this is the way we've got around it. But the Australians, being sticklers, of course, they wouldn't accept that. But you get away with that kind of thing in Africa.
Okay.
Hello.
Yeah. Questions? Someone had a question there.
For aggregate quarries, you should be able to do overburden surveys to find where fresh rock is and how deep it is and the behavior of your overburden removal.
Sorry, what's the question? Is that a statement or?
Well, it's a statement which is a question. Is that for aggregate quarries, where you need to know your overburden profile, because the aggregates is a low price commodity, so overburden removal is very expensive. Your type of survey should be able to assist in finding the overburden profiles.
Yes, well, yes to the radar, no to the drone. So yes, that's where the radar would come in, and we definitely give that a whirl there. As long as there's no moisture or clay in that overburden, yes, it's a great tool for that. The drone wouldn't help there. It's just going to map the bedrock, you know, magnetism. But yeah, we actually do a lot of quarry work. A lot of what Geofocus does is what we call geotechnical work. So we've branched into geotechnical from exploration, and actually we do quite a lot of quarry work. And in fact, we're going up to the second phase of Katsi Dam now. So the second phase of the Highland Water project is about to take place. And we have got the geophysical contract to do all of the quarries and all of the portal tunnels there. So that's going to be interesting. Definitely going to go up for that and do some fly fishing in the dam.
Bonus.
Yeah.
Okay.
Hello?
Yeah.
George? Can you hear me?
Yes, George.
I've got a question.
Go for it.
You mentioned using the magnetometer in the presence of pylons. Have you used the magnetometer? Well, you mentioned you've done some surveys in the northern Kruger Park. Now, across there are the lines coming from Cabora Bassa down to Pretoria, and those are DC lines. have you used your magnetometer in the presence of those DC lines? Because I think the effect might be rather different.
DC tends not to have a electromagnetic field. You need a changing current. It's got to be AC. So AC makes a huge electromagnetic noise. With DC lines, we pick up the pylons because they're metal. We pick up the cables because they're steel or copper. And they're magnetically susceptible, but they're much better for us than the AC lines. So they have less effect, yeah.
Oh, interesting. Yeah.
Gavin, we were not able to see the video that you played. There was something wrong. Is it possible to play it again?
Yeah, sure. So let me just share screen. It's the screen here, I think. Is that working?
Yep.
Can you see this?
There we go.
Much better.
Okay, so let me just show you the beginning. Okay, let me just show it to you coming back again. So you watch, the guy can just hover at will. Obviously now we're getting a lot of swing. And swing we don't like. But you can see here it's 2 meters above the ground. So this is perfect drone terrain. Here we're flying about 7 meters above the ground. Now you can watch him spin around online. So this would be the end of the survey line. Now just watch him spin. See how easy it is. I mean, these things are fantastic. They really are. And then he just does a new line. So unlike an aircraft, which has to do a huge looping turn, this thing just stops dead, spins around, and off it goes again, which I think is fantastic.
And just interesting, your mix of work, Gavin. I mean, you say you're doing an awful lot for municipalities and town planners and that sort of stuff. Is that sort of 50% plus of your work?
Yeah, I mean, we do. Let me just stop this. Okay, that's better. What are you seeing now? Okay, you're seeing me, I guess.
Yeah,
a lot of what we yeah, we do two things now. We do a lot of sinkholes and solar sites. Solar sites are massive. I mean, there are solar sites going up all over this country, plus wind generator sites. So we have teams almost permanently in the Northern Cape doing the geotechnical work there, usually seismic resistivity. Plus we do exploration. So we've got two arms. We do exploration work and we do geotechnical work, which is quite a nice mix. It was a huge learning curve for me because I did exploration my whole life. So it's been very interesting to learn about the geotechnical side. And I've really enjoyed that. And it's kept the wolf from the door during the exploration downturns. We've had tremendous amount of work, particularly sinkhole work. I mean, there's a law in this country now saying you may not even grade a road, make a dirt road on Dolomite without sinkhole studies. You're not allowed to build anything, not even a wooden house, without sinkhole studies. So it's a good law, but it's meant immense amounts of work for guys with gravimeters. So we just permanently got gravimeters on Dolomite as well. So it's a good business, the geotechnical.
Good stuff. Okay. More questions, gents and ladies? All done for the morning. Okay, thanks, Gavin. That was fantastic. So we really appreciate your time and effort, and good to see that geophysics is progressing and becoming far more powerful than a lot of us have always thought. I guess us old-time geologists like to hit rocks and make holes, but I guess there's a whole new world out there when it comes to geophysics, and it's getting smarter every day.
Yeah, got to move with the time and got to move with the technology. Otherwise, you just get left behind, I guess.
Yeah. Okay. So we
look
forward to.
Thank you very much, everyone. Thank you for watching.
Look forward to seeing you in the Cape sometime.
Yeah, I'll give you guys a shout when I arrive.
Fantastic.
Thanks a lot.
Nice to see you all again. Thanks very much.
Yeah.
Thanks, Gavin. Great talk.
Thank you. Bye-bye.
Excellent.
Thank you, guys.
Thanks, everyone.
Thanks, John.
See you
Have a good
next
day.
week.
Okay.
Keep well.
Penny.
Bye now.